Hello, I'm Christopher, and this is 10 Things I Learned While Building My Own Harness. So, the first thing, this is a pattern that I've been using to build my harness, and it essentially allows me to have 24/7 code implementation, and I can come up with new features and bug fixes as my main agent is working. And essentially, the way this works is I have a prompts directory in my project Git repo. And inside of that prompts directory, I have several subdirectories. So I have a subdirectory for staged prompts, a subdirectory for ready prompts, a subdirectory for complete, and blocked prompts. And essentially, the pattern is this. And I have skills I have three skills. The first two correspond with the skill, and then the first two correspond with their own skill, and then the last two have a shared skill. So the first step in this process is I draft a prompt. And what needs to happen for a drafted prompt? Well, my main goal is to answer all of the load-bearing questions ahead of time. So in my skill to draft a prompt, I'll invoke it with /draft prompt, or if I'm using Codex and my skills are defined as Claude skills, then I'll reference the actual skill.md. My draft prompt skill takes my request for either a feature or a bug fix, and it looks at the code to see what changes are necessary to implement this feature. And what often happens is that there are questions that need to be answered in order to handle that prompt that aren't immediately obvious. But in looking at the code, the agent can determine which questions might need to be answered. So at that point, it investigates the questions or the code, it determines which questions need to be answered, and then it surfaces those questions to me, along with what options I have for the decision that needs to be made, as well as what it recommends given the goals of my project. Once all of those questions are answered, the draft prompt skill will save the prompt in the staged directory. So I might have 3 feature requests and 8 bug fixes. I'll draft a prompt for all of them. They all go into the staged directory. Once I have prompts in the staged directory, I can run my review staged prompts skill. And essentially what this is a second pass, repeating everything in the draft phase, but maybe there are questions that it missed the first time. And it might raise new questions, or it might just promote the prompts into ready. Once prompts are in ready, I have a handle prompt skill. And what the handle prompt skill does is it picks the first prompt that is the smallest that has no dependencies. So if I have prompts A, B, and C, and B and C need A to be implemented first, it won't choose B or C even if they're smaller. So it picks the smallest prompt that can be handled on its own, and it works on it. It moves it out of the ready just into the prompts directory, and that's the active prompt. And then once it's done implementing the prompt, it runs all the tests and moves the prompt file to the complete directory and makes a commit. And then in my harness, I'm also bumping the patched version, which I find is a very useful pattern because then I can always install the master branch of my harness and I can run it. And if I notice problems, I can tell my draft prompt agent, hey, I'm having this problem. It's in this version. And it sees all of the versions that exist in the Git history, and it can check what the prompt is that created that version. So it can also see like maybe there is a bug fix that was implemented after this version was created. So I'm about 510 prompts deep into this harness at this point, and it basically has been 4 weeks of maybe not 24/7, but 12/7 autonomous execution in terms of implementing things. And it can check anywhere in that history to figure out where a bug might have been introduced. So anyway, it's been a very good process for me. And I can request new features even as other ones are being implemented because the draft prompt and the review stage prompt skills don't touch any code. They're only touching the prompts, so I'm not going to interfere with the agent that's actually touching the code. The other thing is that it makes for a great goal because I can basically run /goal, handle all prompts until there are no ready ones left. So this is a really good pattern, so much so that I'm trying to come up with a way that I can bake this into the harness itself, because one thing that is annoying about this is I don't want to have files in my code base for the prompts itself. So the prompts themselves. So like, for example, you might work on a team where you might know your teammates if you're having your own proprietary, just personal prompts in the repo. So I think it would be good if that were part of the harness itself. The second one, think in vector space. So I think I'm going to have a little bit of a harder time communicating this one, but I saw this post on X, which I thought was phenomenal, from TSZZL. The greatest white pill of all is that local minima are rare in high dimensional spaces. And this was kind of the tweet or X post that got me thinking about LLMs more in terms of manipulating vector addition than anything else. And the way that I like to think about this is, so when you have an LLM, generally speaking, the way people speak about it, and I know like there are some people who contest the terminology here, but from what I've seen, there's the pre-training phase, and this is like the building the model itself phase. And then there's the post-training phase, which is when you see people doing like fine tunes of local models, that's essentially what the post-training phase is. The pre-training and post-training phase are essentially determining the weights of the model. And this is like the brain of the model. The way that I like to think about my harness and my agents.md or Claude.md or whatever you're using is it is essentially determining what 0, 0 is in the vector space of your harness. So you can think about it like all of your tool definitions, all of your MCP definitions, your agents.md, these are all adding vectors to each other. So your initial starting point for your agent when it starts doing work in your project, in your harness, is different than the model's origin. So ideally, you want to be able to determine the vector additions that you need to make to get to that desired 0, 0 in as few tokens as possible. And essentially your new 0, 0, your new origin is the point from which all work will be done by your LLM in your harness. I think thinking about things this way is more effective than just saying like, how can I save tokens? Which is a useful thing to think about, but I guess maybe I need to do some more thought about this myself to be able to explain this better. But maybe I'll do some X posts about this after I'm able to give it some more thought. The third thing, so my harness, when I set out to build it, my primary goal was to make it as usable as possible with small models, because I don't want to have a situation where Anthropic or OpenAI or a frontier lab will say, decides that actually we're losing too much money, we're going to jack up the prices of our models, or we're going to get rid of our subscriptions, now everyone has to do API pricing. So as part of my thesis for developing my own harness to work with small models, I had this idea that I introduced to my harness called pruning. And the idea of pruning is there is information in the context window that deterministically I can know to be stale and therefore can be removed from the context window. The problem with this that I have found after actually using my harness, which is an interesting learning point, but also a little bit disappointing that my strategy wasn't as effective as I hoped, is most of the tokens your agent uses are spent exploring. So one of the main pruning ideas I had is that if an agent reads a file and then edits that same file, that read is now stale. So it doesn't do the agent any good having the old version of the file in the context window. So in pruning, it can be deterministically removed from the context window and therefore live as much as possible in the early side of the context window instead of the later side of the context window. The problem is that you don't really regain that much context by pruning those files. And if you're using a frontier LLM, you're going to break cache, which is going to be expensive in terms of token spend. So it's kind of a bummer, but this has kind of proven to be an important finding, is that every time you're doing something new, the agent's going to have to explore the code base again. I have seen some experimentation to suggest that you can cache that exploration phase. I don't know how much I like that conceptually at this point, because it might be the case that you have different surface areas in your code base that need to be modified for different tasks. And as such, maybe it doesn't make sense to cache the exploration phase, because like you might explore the wrong part of the code base and now you've burned up that much of the context window to explore something that's not relevant to the task at hand. Now, if you're using a frontier model and you are just going to rely on that cached input, then maybe that makes sense and you can probably save a lot that way. If you're trying to build a harness like I am to work with small models and be defensive against the pitfalls of small models, then you want to optimize that context as much as possible. So I don't know how much sense that makes for my use case. The fourth thing. So I think anything that can be deterministic should be deterministic. And this kind of corresponds with my next point as well, which I'll kind of go to this and talk about these together. Big models are really good at exploring, but it might be overkill once you have an established process for a task. So if you take these two ideas, anything that can be deterministic should be deterministic, and anything that can be done with a small model should be done with a small model. A lot of the systems that you build, like for example, you might have some skills that you run with Opus 4.8 or GPT 5.5, where the decisions that the model needs to make are actually not that complex. And probably the same skill can be accomplished with a much cheaper model. And also probably some of the things that the skill does can be done deterministically instead of via an LLM in a harness. So with that in mind, when you're developing a process, so not like actively writing code for a code base, for example, but like if you have a repeatable process, like if you're trying to build an AI system that's going to write blog posts for you, or you're trying to build an AI system that's going to generate images for you, and you want them to be consistent for your branding, you might want to use a big model to figure out what does that process look like. But once that process is established, you can probably get all of those same things done with much smaller models and deterministic workflows, or, as deterministic as possible, because there's still probably some amount of decision making that needs to happen that doesn't necessarily need to be done by a human. Okay. Some of the differences between frontier models and small models. So as I've been working on my harness, it's designed to be useful with small models, but ideally I want anyone to be able to use the harness with whatever model they want. And there are a couple differences that I've noticed as I've worked with both small models and frontier models. So with frontier models, if you're developing a harness, you can largely lean on the intelligence of the model. So it might be the case that you can use maybe less verbose tool definitions and just assume that the model will get things right, and you'll probably be fine. If you're building for small models, then there are going to be a lot of biases in the model itself that are going to work against you. So one of the things I found is I try to use as little context as possible, but with small models, I find that it's actually better to have more verbose tool definitions to essentially guide the model to make the decisions that I want. So for example, I have some tools that are specifically designed to optimize exploration of the code base. A lot of models will just reach for writing bash scripts or bash commands and use that to explore the code base. And this can be effective, but for the tools that I've designed to specifically search the code base in as token efficient of a manner as possible, if the models aren't using those, they're essentially wasting that tool definition and they're burning more tokens than necessary using a technique that isn't optimized for token usage. So as such, I have found that if I am using my harness with small models, I need more verbose tool definitions, and that eats into the context window. At the same time, if I'm running a model locally, if it takes a little bit longer, that's okay. That's not really the end of the world. I am willing to break cache if I can get more intelligence out of a small model. For frontier models, you don't want to break cache because that's expensive, but you can lean on the intelligence. So if you're designing your harness to work with frontier models, just don't worry about breaking, don't prune, don't break the cache. Just go until you reach the end of your context window and then compact, and you'll probably be fine. Okay, this is a very straightforward one. So subagent handoffs cost 4 times the amount of tokens. So what do I mean by this? When you have a subagent, your orchestrator needs to write the handoff prompt. So that's 1x token usage. The subagent then needs to ingest the handoff prompt. So that's 2x token usage. And then the subagent will write a summary, 3x token usage, and 4, the orchestrator ingests the summary. So there are 4 places where tokens get burned specifically for using subagents. This is not to say that subagents are useless. I think it's just a very important thing to keep in mind where you're developing a system that might be considering, like, are subagents the effective choice here? Maybe they are, maybe they aren't. It's a little bit different between if you're self-hosting a model versus using a frontier model. So if you're self-hosting a model and you don't care about breaking cache, then what you can do is the orchestrator writes the prompt, the subagent ingests it, does its work, writes a summary, and then when the subagent returns to the orchestrator, you can simply remove the handoff prompt with the summary and essentially save half of the tokens from your context window for that whole handoff. Because my thinking with this, and maybe it might depend on your use case, but my thinking is that the summary is probably going to contain all the relevant information from the handoff itself, but then any decisions that were made in the process of handling that handoff prompt. So probably the handoff prompt is redundant at that point. Okay. Point number 8. I think Anthropic is onto this, and I think more people will catch on soon. So the idea of this one is every problem gets a harness. So right now, when people are designing systems to use agentic tools, very often it's building on top of Claude Code or building on top of Codex or building on top of Pi is probably the best choice here because it is so extensible. So it's kind of maybe less approachable for new users who are just trying to write code. But if you're building an agentic process, your own dedicated harness, then Pi makes a lot of sense here. So Claude has introduced dynamic workflows, and that's kind of their iteration on this. This is kind of my take on what I think building workflows with AI will look like. So the first thing is simply proof of concept, your idea with a coding agent. And this is where maybe use GPT 5.5, GLM 5.2, Opus 4.8. Just really reach for the most intelligence you can and figure out what does the workflow that I want to accomplish actually look like. At that point, you have a repeatable process after you figured out how to do it. You can turn that workflow into a skill. So now you have a repeatable process that you can easily invoke in your harness of choice. Once it's a skill, you can then turn it into a dedicated harness. And this is, as far as I can tell, what Claude dynamic workflows are. In my harness, the same feature or functionality is done using Pi. So you essentially create a custom Pi config for whatever problem you're trying to solve. And then step 4 would be take that custom harness to handle your specific task and refine it into the smallest viable model so you can run it as cheaply as possible. I think this will be a super effective pattern for solving problems that will be repeatedly invoked, like the solution will be repeatedly invoked, that requires intelligence. So in LLM, like not everything can be deterministic. And it will give you the most effective way to use the cheapest model possible so you can run that same workflow many times over. So, like I said, Claude's implementation is dynamic workflows. I'm building this into my harness. My harness is written in Rust, but my dynamic workflows are using Pi. So I think that makes a lot of sense. And it's more open than, dynamic workflows. So point number 9 is essentially coming from the idea that you don't need to know the language in which you're implementing your project. So I really didn't know Rust before I started working with AI, but now I write basically any of my CLIs or things that will run on device in Rust. I still use TypeScript and React for web apps just because it's a very established ecosystem and I know it pretty well. Maybe I should explore using Rust for those things, but anyway. The point is, it doesn't matter which language you're using. For the most part, if you give your agent good context, you will be able to get good outputs, regardless of which tools you're using to obtain those outputs. So one of the patterns that I have used that I think works exceptionally well is cloning the repositories of my open source dependencies and giving my agent access to those so it can see how the dependency works under the hood instead of reading docs, which it might get from an untrustworthy source or something like that. It's very consistent because I just clone the Git repo and now I have the latest code for whatever my dependency is. I like this pattern so much that I designed a CLI for it that I can invoke from any harness, and I'm baking this feature directly into my harness. So the first thing you can do is just clone your dependencies into your project. That gets a little messy. You have to make sure you don't commit them, or you bloat your Git repository. But it's a primitive way to get started. I think my CLI implementation was pretty good, but now I'm trying to bake it into my harness itself. So anyway, the point is you don't need to know the programming language you're using. If you give your agent good context, it'll probably be able to figure it out. Point number 10, Grok is great for research. If I am contemplating a feature, but I'm not exactly sure how it will work, usually my workflow is something like go to X, open Grok, ask Grok about whatever feature I want to implement, which packages it might use. And then once I have an idea, roughly speaking, of what that might look like, I will clone the repositories of those packages onto my machine and investigate the source code directly with Codex or MyHarness or whatever I'm choosing to use. So if you're not using Grok yet, I have found that it's great for research. Now that I've showed Grok, if you want to follow me and see my harness, which I plan on releasing soon, you can follow me on X. My handle is CapitCode. Anyway, thank you for watching this video. I hope it was helpful, and I will see you in the next one.